Welcome to this explainer on networking and data flow. So today we're tackling a massive challenge in modern tech. How do we manage massive, highly dynamic fog computing networks without having them completely collapse under the weight of their own latency? We're relying on some truly fantastic source material today to break down the highly complex architecture that makes modern edge networking even possible.
All right, let's jump straight into the roadmap for today. We're covering the fog dilemma, SDN as the brain and muscle, decoding OpenFlow, virtualizing network functions, and wrapping it all up with the ultimate fog synergy. Let's get to it.
Section 1. The Fog Dilemma. Let's quickly set the stage and look at the sheer, absolute chaos of a modern fog computing environment. Imagine just for a second a bustling smart city. You've got literally thousands of dynamic nodes out there. We're talking smart vehicles, roadside routers, local edge gateways, and they're all constantly connecting, disconnecting, and zipping around. Now, if you try to manage all that using traditional hard-coded networking, your network is going to completely drown. It'll just collapse under this massive configuration debt and crippling latency, because every single time a node moves, the routing paths have to change. So that brings us to the million-dollar question. How on earth do you route thousands of smart vehicles without the whole network just falling apart? Section 2. SDN, Brain and Muscle. To actually solve this scaling nightmare, we've got to fundamentally change the anatomy of our network. Let's talk about software-defined networking. This right here is a massive paradigm shift. See, in a traditional networking setup, every single router contains both the routing brain, which we call the control plane, and the forwarding muscle, the data plane. They're totally trapped together inside this one closed proprietary box. The brain has to sit there and run these incredibly complex routing protocols locally just to build its tables, while the muscle physically pushes the packets along. And since every traditional router is basically out there making its own independent decisions, managing a massive fog network like that smart city we just talked about, total nightmare. But SDN breaks this old, clunky design. It completely separates the two, essentially ripping that control plane out and pulling it up into a centralized software engine. What we get from that is this really clean three-tier architecture. Up at the top, you've got the application layer. That's where your network management programs live. In the middle, there's the control layer. This is your centralized SDN controller, and it has a global God's eye view of the entire network. Then, down at the bottom, you have the infrastructure layer. Now, these physical switches, they've essentially become dumb forwarding devices. They contain absolutely zero routing logic. None. They just blindly follow instructions stored in their local flow tables. And honestly, it's exactly this separation that gives us the sheer agility we need to manage thousands of moving parts. Moving on to Section 3, Decoding OpenFlow. So, we've successfully separated the brain and the muscle, right? Let's figure out how this centralized brain actually talks to the muscle down below.
Well, the absolute gold standard for this, what we call a southbound protocol, is OpenFlow. When that central controller needs to boss around those dumb switches at the bottom, it uses this open standard protocol to do it. And what's super cool is that inside an OpenFlow-enabled switch, those traditional MAC and IP lookup tables you're probably used to seeing, tossed right out the window, gone. Instead, they're completely replaced by flow tables, which are just vastly more flexible and programmable.
Let's actually track a data packet's journey through one of these switches step by step. First off, the packet arrives at the switch port, boom. Second, the switch does a quick table lookup, basically comparing the packet's header against its match fields. Third, if it finds a match, which is what we call a flow hit, the switch just executes a specific action, like forwarding it out a certain port, and it ticks up its counter metric. Pretty straightforward. But what if it doesn't find a match? Well, that brings us to step 4, the flow miss. And a flow miss directly triggers step 5, which is rule installation. Let's drill down into that for a second, because a flow miss is a huge, critical event in this whole architecture. When a packet doesn't match any existing entry, this dumb switch is, basically stuck. It literally has no idea what to do with it. So it grabs the packet header, wraps it up into an OpenFlow packet in message, and ships it all the way up to the centralized brain, the SDN controller. The controller looks at it, decides the optimal path, creates a new rule, and then sends a message right back down to install that brand new forwarding rule directly into the switch's table. Now, if you look at the math, this flow miss creates a pretty major delay penalty. It's kind of like a low-level employee having to call the CEO at headquarters every single time they get a new task. The total delay is going to equal the lookup time plus the round-trip propagation time, because remember, that message has to travel all the way up to the controller and back down again, plus the actual time it takes the controller to process it. In a massive, sprawling fog network, that propagation time, it can be an absolute killer if your central controller is too far away. And honestly, this is exactly why fog computing nodes will often host local subcontrollers right there at the edge. It keeps that propagation time near zero, ensuring the network stays lightning fast even when it's constantly getting hit with brand new traffic flows. All right, Section 4, Virtualizing Network Functions. So we've successfully fixed the routing logic, but we still really need to talk about the physical hardware side of things. Let's get into virtualization. Historically speaking, if you wanted a firewall, an intrusion detection system, and a load balancer at your fog gateway, you'd literally have to go out and buy 3 completely separate, ridiculously expensive hardware boxes from proprietary vendors. But Network Functions Virtualization, or NFV for short, totally changes the game here. It takes all those dedicated hardware appliances and just replaces them with software. We call these virtual network functions, or VNFs, and they run on totally standard commercial off-the-shelf servers. Seriously, no more buying specialized metal boxes. You literally just spin up the software on a standard high-performance server right there at the edge. Which brings us to Section 5, the ultimate fog synergy. This is the best part. Let's see how SDN and NFV actually team up in the real world to solve that original fog dilemma we talked about. Let's jump back to that smart highway example from earlier. Picture thousands of connected cars just driving along, and suddenly, boom, traffic completely spikes in one specific sector. Here's what happens. NFV provides that flexible network functionality by instantaneously spinning up virtual firewalls and virtual routing functions directly on the local roadside edge servers to handle the massive load. Meanwhile, SDN swoops in to provide the agile routing control. It dynamically steers all that crazy traffic right through those newly created virtual firewalls using our good friend OpenFlow rules. So think about it. You've got software creating the tools on demand and a centralized brain seamlessly routing traffic through them. The best part? All of this happens without a single technician ever needing to drive out and visit a physical site. It's brilliant. All right, the masterclass matrix. Just to make sure these foundational concepts really stick, let's do a quick side-by-side comparison of SDN versus NFV. Let's summarize exactly what we've learned here. The core goal of traditional networking was distributed, manual routing that was deeply embedded in the hardware itself. Sure, it gave us great stability, but terrible, terrible flexibility. Then SDN comes along, right? Its whole goal is to decouple the control plane from the data plane. It moves that intelligence up to a centralized controller to give us ultimate programmable control over the network. Meanwhile, NFV is running parallel to this. Its goal is to decouple the network functions from the physical hardware, moving them onto virtual machines to just drastically slash those hardware costs. So they're technically solving 2 entirely different problems, but when you put them together, absolute powerhouse. Which leaves us with this final thought to chew on. By implementing SDN and NFV, we've basically taken the brain and the muscle of the network, totally separated them, and virtualized all the heavy lifting. And you know, this isn't just some neat party trick, it's the absolute prerequisite for the future of networking. With this incredibly agile, software-defined foundation now locked in, how do you think this architecture is going to handle the massive leap to true 5G, multi-access edge computing, and dynamically slicing up the network for totally different applications? The foundation is built for sure, but the real revolution? It's literally just getting started. Thanks so much for joining me on this explainer, and hey, keep questioning how the systems around you are actually built.